Welcome, and thank you for joining this quiet exploration. Here, curiosity is not rushed, and science is not treated as a race but as a companion for reflection. Perhaps you are listening at the end of a long day, letting your thoughts drift before sleep, or maybe you are simply searching for a different way of seeing the familiar world around you. Wherever you are, I am glad you are here. Tonight, we will follow a question, not one that offers quick answers or neat conclusions, but one that stretches the imagination and invites us to look at the ground beneath our feet with new eyes. The question is simple to ask yet vast in implication. How did the oceans, the endless waters that dominate our planet, come to be? The Earth we know today is defined by water. Seen from space, our planet gleams with vast blue expanses that cover more than 70% of its surface. Oceans regulate our climate, feed our atmosphere, and cradle nearly all forms of life. Yet, if we could travel back to the Earth's earliest days, we would find a world almost unrecognizable. The young planet was not a calm water world, but a blazing sphere wrapped in molten rock, its skies choked with volcanic gases, and its surface endlessly reshaped by violent impacts from space. In this primeval environment, oceans did not exist, but the seeds of their birth were already waiting, carried in vapor, rock, and ice. The story of the oceans begins with fire. Early Earth was a restless planet, its crust thin, fractured, and unsettled. Volcanoes erupted constantly, pouring out rivers of lava and releasing vast clouds of steam and gases. Among these gases were hydrogen and oxygen, the raw ingredients of water. For millions of years, they gathered in the thick atmosphere, trapped beneath a veil of carbon dioxide, nitrogen, and methane. As the surface slowly cooled, water vapor condensed and began to fall as rain. But this was no ordinary storm. It was a rain that lasted for thousands upon thousands of years, a relentless downpour that filled every lowland, carved channels into the glowing crust, and slowly collected into the first ancient seas. Even before the first rain fell, the planet was already receiving water from beyond its skies. Asteroids and comets, rich in ice, struck Earth with tremendous force. Each impact delivered more of the precious molecules that would one day flow together as oceans. Some scientists argue that much of Earth's water was born this way, carried across the void of space, while others believe it was always hidden within the planet itself, locked deep in minerals until volcanic heat released it. Perhaps the truth lies in both. However it arrived, the water accumulated, drop by drop, wave by wave, until Earth was no longer a dry world but a blue one. But these first oceans were not like the transparent waters we imagine when we picture a beach or a lagoon. They were heavy with dissolved metals, thick with minerals drawn from the fresh crust, and often colored red or green by chemical reactions unfamiliar to us today. Sunlight struggled to pierce their depths, and yet, within this murky broth, the foundations of life were quietly being laid, deep beneath the surface, at cracks where seawater met the hot mantle below. Hydrothermal vents erupted. They spewed streams of superheated water, dense with minerals, into the surrounding sea. Here, simple molecules collided and combined in countless variations. Over unimaginable spans of time, some of these combinations became stable and complex, forming the earliest building blocks of biology. Many scientists believe it was in these dark vent systems that the first primitive cells took shape, beginning a story that still continues in every living organism today. The oceans did more than cradle life. They began to sculpt the character of the entire planet. Rain washed minerals from the land, carrying them into the seas, where they dissolved and altered the chemistry of the water. Slowly, the oceans grew salty. Rivers carved valleys into the land, shaping the continents even as they enriched the seas. And as the oceans expanded, they became engines of climate, absorbing carbon dioxide, moderating surface temperatures, and driving weather patterns. Without these vast waters, Earth would have remained unstable and barren. With them, it became fertile, habitable, and alive. Through the passage of ages, the oceans never stayed the same. They ebbed and flowed with the shifting of ice and heat. During ice ages, great sheets of frozen water spread across the continents, locking up vast quantities of the sea and lowering global levels. When the ice melted, the seas returned, sometimes flooding coastlines and redrawing the borders of continents. These cycles were not small fluctuations. They were dramatic events that shaped the fates of species, opening pathways for migration in one era and drowning entire landscapes in another. Even the floor of the ocean itself was not permanent. The crust beneath the seas cracked and drifted, pulled by the slow churn of tectonic plates. New ocean basins opened as continents split apart, while others closed when landmasses collided. The Atlantic Ocean, still young in geological terms, grows wider with each passing year, while the Pacific slowly narrows. Long before humans appeared, ancient oceans had already lived and died. Panthalassa, the vast ocean that surrounded the supercontinent Pangaea, once covered most of the globe. Before that, other oceans had spread and vanished, each leaving behind clues in the rocks for geologists to uncover. Within these waters, life itself evolved in step with the ocean's transformations. Early microscopic organisms filled the seas with oxygen, slowly changing the atmosphere and paving the way for more complex forms. In shallow waters, algae and corals created reefs, intricate structures that became homes to countless species. In deeper waters, strange creatures adapted to darkness and pressure, forming ecosystems as alien to us as distant planets. Over millions of years, fish appeared, then amphibians, and eventually the ancestors of every land-dwelling creature ventured from the seas onto dry ground. The oceans were not merely a backdrop to evolution, they were its driving force. When we look at the oceans today, their surface may seem timeless, but in truth they are still changing. Currents circle the globe, redistributing heat and shaping climates. Storms draw their energy from warm waters. The chemistry of the seas continues to shift, responding to both natural cycles and human influence. Just as in the past, the oceans remain at the heart of Earth's story, both fragile and resilient. Ancient yet always new to it is humbling to consider that each wave that washes onto a shore carries with it the memory of an origin billions of years ago. The salt in its foam is the salt of ancient rivers, the minerals of vanished mountains. The winds that push the tides are guided by patterns that began when Earth's first seas cooled. To listen to the ocean is, in a way, to hear the heartbeat of the planet, a rhythm that began with fire, rain, and the endless patience of time. The birth and evolution of the oceans is not just a chapter in Earth's history. It is the foundation of every other chapter. Without them, there would be no forests, no animals, no humans. There would be no clouds drifting across the sky, no rain nourishing the soil, no rivers carving their way to the sea. The oceans are not merely part of the earth. They are the essence of it, the element that defines it as the water world we call home. And so, when we look at the horizon and see the sun glinting off the endless blue, we are not just looking at water. We are looking at the planet's deepest memory, its oldest story, and its greatest gift. The story of the oceans did not end with their birth. Once the waters had gathered, their history became one of endless transformation. The oceans were never still, never fixed. They expanded and contracted, rose and fell, split and merged in response to the restless shifting of Earth's crust. To understand their evolution is to watch the slow dance of continents across billions of years, a choreography written in stone and water that in the deep past. Long before the continents formed the outlines we know today, there were other worlds of land and sea. Each supercontinent was surrounded by vast oceans, and each supercontinent eventually broke apart, reshaping the map of the seas. The largest of these ancient bodies was Panthalassa, the great ocean that covered nearly the entire planet during the Age of Pangaea. Its waters stretched from pole to pole, a single, uninterrupted expanse surrounding the united landmass. No modern ocean compares to its scale. Within its depths, countless marine creatures evolved, adapted, and vanished, leaving behind only fossils as traces of their time in that boundless sea. Alongside Panthalassa lay another important ocean, the Tethys Sea, which opened between the northern and southern landmasses. The Tethys was smaller than Panthalassa, but it played a critical role in the history of life. Its warm, shallow waters became a cradle of biodiversity, home to coral reefs, early marine reptiles, and fish that would shape evolutionary pathways for millions of years. As the continents shifted, the Tethys slowly closed, its remnants surviving today as the Mediterranean, the Black Sea, and parts of the Indian Ocean. These transformations remind us that oceans are not permanent features. They are temporary expressions of deeper forces, appearing and disappearing over spans of geological time. Where today the Atlantic Ocean grows wider every year, tomorrow, measured in millions of years, it may close again. Where the Pacific now dominates, someday it may vanish entirely, consumed as continents drift together once more. Oceans are born in rifts, widen into seas, and eventually fade into memory, just as countless others have before them. But oceans are not just boundaries of geography. They are engines of climate. When vast superoceans exist, global circulation is different. Winds sweep across their open surfaces without interruption. Storms can grow immense, unbroken by land. Currents move heat across the globe in unfamiliar patterns, creating climates far harsher in some regions and far milder in others. Panthalassa, for example, likely drove powerful currents that influenced the interior of Pangaea, shaping its deserts and monsoon systems. The presence or absence of certain oceans has always guided the rhythms of temperature, rainfall, and storm. The ice ages brought another layer of change. When glaciers grew across continents, oceans withdrew, their waters locked away in frozen sheets of ice. Shorelines moved outward, exposing vast stretches of land that had once been seabed. These exposed areas became pathways for migration, allowing animals and much later humans to cross from one continent to another. When the ice melted, the seas rose again, drowning coasts, swallowing river valleys, and remaking familiar landscapes. Each cycle of ice and thaw was written in the oceans, and each cycle reshaped the story of life. Throughout these transformations, the oceans remained the stage on which life evolved. Early in their history, they were dominated by single-celled organisms that filled the water with oxygen. Later, in the Cambrian period, the seas exploded with diversity. Trilobites crawled along the seabed. Strange armored fish swam through shallow lagoons. Later still, giant marine reptiles ruled the waters of the Mesozoic, from long-necked plesiosaurs to powerful mosasaurs. The oceans became laboratories of adaptation, testing life in countless forms and scales. Every great evolutionary leap began in water, carried forward by the tides of time. Even the chemistry of the oceans changed. At first, they were rich in iron, giving them a reddish hue. Over time, as oxygen filled the atmosphere, the iron oxidized and settled into the seafloor, leaving the waters clearer and paving the way for the blue oceans we know today. The balance of gases, the concentration of salt, the cycling of nutrients all evolved alongside life itself. The oceans were never passive containers but active participants, shaping biology even as biology reshaped them. Modern oceans still bear the imprint of this long history. The Atlantic, with its widening rift at the mid-Atlantic ridge, is a reminder of how seas are born. The Pacific, ringed with trenches and volcanoes, reflects the slow closing of an ancient ocean basin. The Indian Ocean carries the memory of the Tethys, while the Arctic and Southern Oceans remind us of the role of ice in sculpting the planet. Each current, each tide, each coastline is part of a story that began billions of years ago and continues in every wave. To stand at the edge of the sea today is to look into deep time. The horizon may seem calm, but beneath its surface lies a record of fire and ice, collision and drift, birth and extinction. The oceans are storytellers, their waves whispering of ages when the planet was different, when continents were joined in unfamiliar shapes, when life itself was just beginning to find its way. They are not only the waters of the present but the memory of the earth itself, carrying within them the imprint of every change that has ever come to pass. As vast and ancient as they are, they remain works in progress, reshaped with every passing moment. To imagine their future is to look ahead into deep time, far beyond the scale of a single lifetime or even the span of human history. The oceans we know today, the Atlantic, the Pacific, the Indian, the Southern, the Arctic, are only temporary chapters in a story that stretches both backward and forward for billions of years. Continents never rest. They drift upon the slow, flowing mantle beneath, pulled apart by spreading ridges and pushed together by subduction zones. This motion will continue for as long as Earth remains geologically alive. And with each shift, the oceans will change. The Atlantic, still young in geological terms, is widening as the seafloor spreads at its center. Its coastlines drift farther apart year by year, carrying Europe and the Americas away from each other. The Pacific, by contrast, is shrinking. Around its margins, tectonic plates are being consumed back into the mantle, slowly closing the vast ocean that once dominated the globe at tens of millions of years. These movements may lead to the birth of a new supercontinent. Scientists have given names to some possibilities: Amasia, formed near the North Pole; Orica, gathering continents around the equator; or Nova Pangaea, a landmass uniting the Americas with Asia and Australia. Each scenario would reshape the oceans entirely, closing some while opening new ones. The coastlines familiar to us would vanish, replaced by shorelines we cannot fully picture. For the oceans, it would be the same cycle repeated again: expansion, closure, transformation. But the future of the seas will not be guided by geology alone. Climate, too, will play its part. Already, the oceans are changing under the influence of human activity. They absorb much of the heat trapped by greenhouse gases, warming at depths once thought immune to change. Currents shift, storms grow stronger, and ice melts into rising seas. The chemistry of the oceans is also shifting. As carbon dioxide dissolves in water, it alters the delicate balance of acidity, affecting coral reefs, plankton, and the countless species that depend on them. These changes are rapid on geological timescales, unfolding within mere centuries instead of millions of years. If warming continues, the oceans may take on unfamiliar states. Ice sheets in Greenland and Antarctica could collapse, raising sea levels by tens of meters. Coastal cities, river deltas, and island nations would be reshaped or erased, their histories drowned beneath encroaching tides. New coastlines would emerge, but they would not resemble the world we know. Ocean currents, the conveyors of global climate, could weaken or redirect, altering rainfall patterns and shifting the balance of deserts and fertile lands. For humanity, the future of the oceans will be inseparable from the future of civilization itself. Yet beyond the human scale, the oceans will persist. Even if coastlines change, even if species vanish or adapt, the waters will continue their endless cycles of evaporation, rain, and return. Over millions of years, the scars of the present will be folded into new patterns, part of the ongoing rhythm of Earth. New life may rise to fill niches left empty. Coral reefs may return in unfamiliar forms. Fish, mammals, or creatures we cannot imagine may thrive in seas reshaped by time. Far ahead, as tectonic forces gather the continents together once more, the oceans may contract into a single superocean. Perhaps it will resemble Panthalassa, a vast body encircling one great landmass. Or perhaps smaller seas will remain, scattered across the surface like fragments of memory. Either way, the cycle will continue, repeating the ancient story of birth and loss, expansion and closure. The ultimate fate of Earth's oceans lies still further ahead. In billions of years, as the sun grows hotter, evaporation will outpace replenishment. The seas will retreat, shrinking under a thickening atmosphere. The oceans that once covered most of the planet will vanish, leaving behind dry basins, salt flats, and relics of their former greatness. Eventually, Earth may resemble Venus, parched and unrecognizable, its oceans remembered only in stone and in the traces of life they once nurtured. But that distant end lies far beyond the scale of human imagination. For now, the oceans remain alive, dynamic, and full of change. Their tides still move with the pull of the moon. Their currents still trace invisible rivers across the globe, and their waves still carry the stories of the past into the present. To stand beside them today is to glimpse not only their ancient history but also their unfolding future. A reminder that nothing on Earth is truly permanent, yet everything is part of a greater continuity. The oceans have always been, and will always be, the beating heart of our planet. They are the mirror of Earth's past and the canvas of its future. In their depths lies both memory and possibility, waiting to be discovered, waiting to be imagined, waiting to be heard. Beneath the calm surface of the seas, beneath the shifting tides and the rolling waves, lies a world almost entirely hidden from human eyes. For centuries, the oceans seemed infinite and impenetrable, their true depths unreachable. Sailors spoke of monsters dwelling in the abyss, and myths painted the deep as a place beyond comprehension. Today, science has replaced myth with knowledge, yet the mystery has not vanished. The truth is that the majority of Earth's ocean floor remains unexplored, mapped only in the broadest outlines. What lies beneath continues to invite both curiosity and humility. The ocean is vast not only in surface area but also in depth. While its average depth is around 4 kilometers, some regions plunge far deeper. The Mariana Trench, the deepest known place on Earth, descends nearly 11 kilometers, a chasm so extreme that if Mount Everest were placed within it, its peak would still be drowned beneath more than a kilometer of water. In such places, sunlight cannot penetrate and pressure mounts to unimaginable levels, over 1,000 times greater than at the surface. To humans, it is utterly hostile. To other forms of life, however, it is home. For centuries, it was assumed that such depths must be barren. Without sunlight, photosynthesis could not occur. Without photosynthesis, life seemed impossible. But the discovery of hydrothermal vents along the mid-ocean ridges transformed that belief. These vents, where seawater meets molten rock, spew mineral-rich fluids into the darkness. Around them thrive entire ecosystems, built not on sunlight but on chemical energy. Tube worms longer than a human body, ghostly white crabs, and strange fish gather in dense communities, sustained by bacteria that feed on sulfur compounds. It was a revelation. Life could exist in places once thought utterly lifeless. Beyond hydrothermal vents, the deep sea is home to an astonishing variety of creatures. Many produce their own light through bioluminescence, tiny flashes and pulses that shimmer in the dark. For some, light is a lure to attract prey. For others, a signal to potential mates. Some use it as camouflage, masking their silhouette against the faint glow from above. The result is a living constellation, a starfield drifting through black waters. The shapes of deep-sea creatures are often bizarre to human eyes. The anglerfish dangles a glowing lure before its mouth, drawing in the unwary. The gulper eel can expand its jaw to swallow prey larger than itself. Giant squids, once the stuff of sailors' legends, roam the depths with eyes the size of dinner plates. Eyes evolved to capture the faintest hint of light. Even microscopic organisms, unseen by the naked eye, form intricate skeletons of glassy silica or delicate calcium, raining down through the water to carpet the seafloor in endless drifts of sediment. But the deep ocean is not uniform. It is layered, structured by pressure, temperature, and salinity. The uppermost zone, where sunlight still reaches, teems with plankton, fish, and marine mammals. Below it lies the twilight zone, dimly lit and cooler, home to creatures that migrate upward each night in the greatest animal movement on Earth. Still deeper is the midnight zone, where light vanishes entirely, and beyond that, the abyssal plains stretch dark and silent for thousands of kilometers. Here, only occasional seamounts or volcanic ridges break the monotony. Finally, in the Hadal Zone, the trenches, life persists in the most extreme conditions imaginable. Each zone is like a world unto itself, layered atop the others, connected yet distinct. What makes the deep ocean so compelling is not only its strangeness but also its scale. It covers more of Earth's surface than all continents combined. It holds more life than we can measure, more carbon than all forests, and more secrets than any other part of the planet. Its ecosystems regulate the climate, cycle nutrients, and shape the chemistry of the atmosphere. Yet, despite its importance, it remains the least explored. More people have walked on the moon than have reached the deepest trenches of Earth. Technology is slowly changing that. Submersibles, remotely operated vehicles, and autonomous drones now descend to depths once beyond reach. They send back images of alien landscapes, fields of black smokers venting clouds of minerals, ghostly fish hovering in the dark, delicate corals growing on undersea mountains. Each expedition reveals species never before seen, expanding our understanding of what life can be. But even with these advances, exploration has barely begun. The deep sea is so immense that at the current pace, it would take centuries to survey it all. There is also fragility beneath the waves. Deep-sea ecosystems, though remote, are not immune to human impact. Mining interests eye the mineral-rich nodules scattered across abyssal plains. Industrial fishing drags nets across seafloors, destroying habitats that took millennia to grow. Climate change warms even the deep, altering oxygen levels and stressing life adapted to stability. The very regions that seem most eternal are, in truth, vulnerable. Protecting them requires more than technology. It requires restraint, humility, and a recognition of their irreplaceable value. And yet, in the quiet of the abyss, resilience is evident. Species have endured there for millions of years, weathering changes that reshaped the surface world. They remind us that life is not confined to what we find comfortable. Instead, it adapts, reshapes itself, and endures in forms we struggle to imagine. In the darkness of the deep ocean, life continues its ancient experiment, reminding us of both its fragility and its strength. To listen to the deep ocean is to hear echoes of Earth's earliest times. Long before forests, before dinosaurs, before even the first fish, microbes thrived in mineral-rich waters. Their descendants still live in vent communities, guardians of a lineage stretching back billions of years. They are living reminders of the continuity of life, spanning from the first stirrings of biology to the present. In the silence of the deep, history lingers. The hidden depths of the ocean are not merely a frontier, they are a mirror of possibility. They reveal that life is not bound by sunlight alone, that energy can come from stone and water, that adaptation can take forms stranger than imagination. They suggest that if life can endure here, it may endure elsewhere, in the icy oceans of Europa, in the methane lakes of Titan, or in places we have not yet dreamed. The deep ocean teaches us not only about Earth, but also about the universe as we end our quiet exploration of these depths. One truth becomes clear. The ocean is not an empty void, but a living cosmos beneath our feet. Its darkness is not absence, but presence, filled with light of its own kind, with forms of resilience and beauty still hidden. To rest tonight is to carry that awareness gently, that beneath the surface of the familiar lies a world vast, strange, and enduring, a reminder of the mystery that still surrounds us. The ocean is not just a vast container of water. It is the great engine of Earth's climate. Every wave, every current, every exchange of heat and gas with the atmosphere shapes the conditions in which all life unfolds. To understand the story of climate is to understand the story of the sea, because the two are inseparable, bound in a dance that has lasted for hundreds of millions of years. From the moment the oceans first condensed on Earth's surface, they began their role as regulators. Water absorbs heat more slowly than land, but holds it far longer, creating a stabilizing effect. Without oceans, temperatures on Earth would swing wildly between burning days and freezing nights. With them, the planet's surface remains more balanced, its extremes softened. This buffering role has been essential for life. Without it, complex organisms might never have arisen. Currents act as the arteries of this system. Driven by wind, Earth's rotation, and differences in temperature and salinity, they transport immense amounts of heat around the globe. The Gulf Stream, for example, carries warm waters from the tropics toward Europe, softening its winters and shaping its climate. The Antarctic circumpolar current encircles the southern continent, isolating it in a deep freeze, but also helping to drive global circulation. These flows are invisible from above, yet they influence every coastline, every forest, every desert. The surface is only half the story. Beneath it, in what scientists call the global conveyor belt, currents carry water across entire ocean basins. Warm surface water drifts northward, cools, sinks, and then slowly moves back along the depths, taking centuries to complete a single circuit. Along the way, it carries oxygen, nutrients, and carbon dioxide, linking distant ecosystems. What happens in the North Atlantic, where water sinks into the abyss, can eventually affect the productivity of fisheries in the Pacific. In this way, the ocean is not just local but planetary, knitting together far-flung regions into a single living system. Oceans also breathe with the atmosphere, exchanging gases continuously. They absorb carbon dioxide, some of it dissolving directly, some taken in by phytoplankton that capture it during photosynthesis. When these tiny plants die, a portion of that carbon sinks to the depths, locked away for centuries or millennia. This biological pump is one of the great regulators of Earth's climate. Without it, atmospheric carbon would soar, and the planet would be far hotter than it is today. The air we breathe carries the imprint of plankton drifting in the waves, unseen but essential. And yet, oceans do not only moderate, they also amplify. During El Niño events, when warm water pools in the Pacific, weather patterns ripple across the globe. Rains fail in some places, storms intensify in others. The ocean's heartbeat can be felt on every continent, reminding us of its power. Over longer scales, shifts in circulation have been linked to ice ages, droughts, and abrupt climate events. The seas are not passive but active, shaping the rhythm of time itself. If we look into the deep past, we see how tightly ocean and climate have always been intertwined. When the supercontinent Pangaea stretched across Earth, ocean circulation patterns were different. Vast interiors became deserts, while coasts received monsoon rains. Later, when continents split and new seaways opened, climates shifted again. The closing of the Isthmus of Panama just 3 million years ago redirected currents, strengthening the Gulf Stream and helping trigger the ice ages of the Northern Hemisphere. Small changes in ocean pathways ripple outward into profound transformations for life on land. Today, we stand at another turning point. Human activity is altering the climate at a pace far faster than most natural cycles. The ocean, long our stabilizer, is absorbing over 90% of the excess heat trapped by greenhouse gases. It is also absorbing large amounts of carbon dioxide, changing its chemistry and becoming more acidic. This threatens corals, shell-building creatures, and the delicate balance of marine food webs. Currents, too, may be shifting. There are signs that parts of the Great Conveyor Belt are slowing, with potential consequences for rainfall, storms, and even the stability of ice sheets. And yet, for all its vulnerability, the ocean still holds resilience. It has weathered asteroid impacts, volcanic winters, and the waxing and waning of ice ages. Life has adapted to shifting coastlines and fluctuating seas. The question is not whether the ocean will survive, but how it will change, and whether human societies can adapt alongside it. To live on Earth is to live in conversation with the sea, to recognize that our fates are braided together. The climate of the future will not be written in the sky alone. It will be written in the movement of water, in the quiet exchanges between ocean and air, in the rise and fall of tides that respond to forces far beyond our sight. To pay attention to the ocean is to pay attention to the breath of the planet itself. Its size are slow, measured in decades or centuries, but their consequences reach us all in the stillness of night, when waves are distant and unseen. One might imagine the ocean as a sleeping giant. Yet even in rest, it stirs, currents flowing, heat shifting, life drifting in endless migration. It is not a passive backdrop, but an active presence, one that shapes the very possibility of calm skies and fertile lands. To understand climate is not only to study numbers and charts, but to remember that beneath them lies the sea, vast, restless, and alive. So as we close this reflection, let the ocean's role linger in your thoughts. It is the memory of past climates, the regulator of the present, and the architect of the future. Every drop of rain, every gust of wind, every change of season is touched by its hand. And though much remains uncertain, one truth endures. The ocean breathes for the planet, and in its breath, we find our place. The oceans, in their immense depth and breadth, have always been the cradle of life. From the earliest microorganisms that first stirred in mineral-rich waters to the vast array of species we know today, the story of marine life is a tale of endurance, adaptation, and transformation. To understand the living seas is to trace the journey of evolution itself, as it unfolded beneath the waves. Long before humans walked the land. In the beginning, the seas were dominated by microscopic life. Single-celled organisms drifted in the water, harnessing sunlight or chemical energy, shaping the chemistry of the oceans and, eventually, the atmosphere. Cyanobacteria, for instance, produced oxygen as a byproduct, gradually altering the composition of the air and enabling more complex life to emerge. These tiny architects of change laid the foundation for every future creature. From the smallest plankton to the largest whale, as time passed, multicellular organisms emerged, adding complexity to the marine world. Early animals began to explore new forms, developing shells, spines, and specialized organs. The Cambrian explosion, roughly 540 million years ago, marked a remarkable surge in diversity. Trilobites scuttled across the seabed, their segmented bodies a marvel of adaptation. Strange arthropods and mollusks experimented with shapes and strategies that would echo throughout evolution. Each new form occupied a niche, creating a dynamic, interdependent ecosystem. The seas were not static. Shifting continents, fluctuating climates, and changing chemistry continuously reshaped habitats. Reefs formed, eroded, and formed again, providing shelter and resources for countless species. Coral polyps created intricate frameworks, while algae and seagrasses anchored ecosystems and fueled the food web. Predation and competition drove innovation. Faster swimmers, sharper jaws, better camouflage. The ocean became a laboratory of survival, where natural selection worked ceaselessly, often in ways that would seem alien to human eyes. During the Paleozoic and Mesozoic eras, marine reptiles, enormous fish, and early cephalopods ruled the waves. Ichthyosaurs glided like modern dolphins, their bodies streamlined for speed and agility. Plesiosaurs, with long necks and paddle-like limbs, hunted in the open ocean. Ammonites, coiled like delicate spirals, thrived in vast numbers, only to vanish in mass extinction events that periodically reshaped the seas. Each extinction was both an ending and a beginning, clearing space for new forms to flourish. The deep ocean added another dimension to life's diversity. Hydrothermal vent communities, isolated and extreme, evolved independently of sunlight, relying on chemosynthesis for sustenance. Tube worms, crabs, and clams developed symbiotic relationships with bacteria, illustrating that life could thrive in environments humans once deemed impossible. The abyssal plains, cold and dark, became home to strange creatures. Anglerfish with glowing lures, gelatinous squids, and bizarre crustaceans, all perfectly adapted to crushing pressure and perpetual night. Over millions of years, life radiated outward from the oceans onto land, yet the seas remained the dominant force in the biosphere. Fish diversified into every conceivable form, from tiny filter feeders to predatory sharks. Coral reefs became cities of biodiversity, bustling with thousands of species. The open ocean, once considered empty, teemed with life, from schools of silvery fish to massive whales that traversed thousands of kilometers. Each species played a role in maintaining the balance of the ecosystem, cycling nutrients, regulating populations, and shaping the very chemistry of the water. Human impact, though recent in geological terms, has already altered these patterns. Overfishing, pollution, and climate change are reshaping habitats at unprecedented speed. Coral bleaching events are more frequent, oxygen minimum zones expand, and acidification threatens the very foundations of marine life. Yet even amid these pressures, resilience persists. Some species adapt quickly, moving to new regions, altering reproductive strategies, or forming symbiotic partnerships to survive. The living seas are both vulnerable and extraordinarily dynamic, capable of responding to change in ways we are only beginning to understand. The oceans are not merely habitats, they are storytellers. Every fossil preserved in sediment tells a tale of adaptation, survival, and extinction. Every living species carries genetic echoes of ancestors that navigated seas vastly different from those we see today. By studying them, we uncover lessons about resilience, innovation, and the profound interconnectedness of life. The evolution of marine life is a testament to the power of slow, persistent change, guided by the invisible hand of natural selection and shaped by forces beyond the control of any single creature. The seas also remind us of scale. In the vastness of the oceans, life can appear both abundant and fragile. Plankton blooms, invisible from the surface, fuel entire food chains. Deep-sea creatures, hidden in darkness, maintain cycles that influence the climate and chemistry of surface waters. Coral reefs, though small in area compared to open oceans, support an astonishing proportion of biodiversity. These patterns illustrate a principle. The health of the oceans depends on balance, on the harmonious interplay of countless organisms, each contributing to the larger system. To imagine the living seas is to imagine a world both alien and familiar. Strange creatures with adaptations that challenge our understanding coexist alongside forms recognizable to us. Dolphins, turtles, and fish that have swum through oceans for millions of years. From the surface to the deepest trenches, life has found a way to persist, adapt, and thrive, turning the ocean into a theater of endless experimentation and innovation. Even now, vast mysteries remain. Scientists estimate that a large majority of marine species are still undiscovered. Entire ecosystems likely exist beyond the reach of modern submersibles, and chemical, genetic, and behavioral adaptations await revelation. The living seas are thus not only a record of the past, but a promise of discovery, a reminder that Earth's story is far from complete. As night falls and waves lap against the shore, the ocean's legacy continues quietly. Beneath the surface, life pulses, feeds, reproduces, and evolves. The tides carry it, the currents shape it, and the cycles of the sun and moon guide it. For those who listen, the oceans whisper the history of the Earth, the triumphs and failures of countless generations of life, and the enduring truth that in water lies the source of abundance, resilience, and wonder. The story of marine life is the story of life itself, a chronicle of adaptation, challenge, and interconnectedness. From the smallest microbe to the largest whale, every organism is part of the continuing narrative, a thread in the living tapestry of the seas. To explore, to study, and to protect this world is to participate in that story, to bear witness to the vastness, complexity, and beauty of the oceans. And so, as we conclude this reflection, we return to the simple yet profound understanding that the oceans are alive in every sense of the word. They are the cradles of life, the keepers of climate, the shapers of landscapes, and the endless reservoirs of mystery. In their depths, life continues, ancient and evolving, a constant reminder that Earth is far more wondrous, dynamic, and interconnected than we can ever fully comprehend. The oceans of the Mesozoic era were worlds unto themselves, vast and teeming with life, shaped by shifting continents, changing climates, and evolving ecosystems. Long before humanity appeared, long before humans imagined continents or borders, these seas were bustling arenas where life experimented with forms and strategies that often seem alien to us today. To understand these oceans is to step back into a time when dinosaurs dominated the land, while the seas were ruled by creatures equally remarkable, equally adapted, and equally diverse. By the early Triassic, following the mass extinction at the end of the Permian, the oceans were still recovering. Life had been nearly wiped out, yet from the depths, new species emerged. Ammonites, coiled-shelled cephalopods, flourished in shallow and deep waters alike, their intricate shells serving as protection and buoyancy. Small fish diversified, some developing features that would later give rise to the familiar forms of modern marine vertebrates. The seas, though less crowded than they would become, already displayed the resilience and innovation that would characterize the Mesozoic. During the Jurassic, the oceans truly came alive. Plesiosaurs, with their long necks and paddle-like limbs, patrolled coastal waters and deeper seas, hunting fish and smaller marine reptiles. Ichthyosaurs, resembling modern dolphins in shape but far larger in some species, sped through open waters. Their streamlined bodies evolved for rapid pursuit of prey. Mosasaurs, the apex predators of the late Cretaceous, could grow more than 15 meters in length, combining power, agility, and intelligence to dominate the food chain. These marine reptiles evolved independently from terrestrial dinosaurs yet mirrored them in ecological impact, demonstrating how evolution adapts to the demands of any environment. But Mesozoic seas were not ruled solely by large predators. Coral reefs expanded in tropical regions, creating complex habitats that sheltered thousands of species. Crustaceans scuttled along the seafloor, bivalves filtered water for nutrients, and tiny plankton drifted in sunlight near the surface, forming the foundation of the food web. This plankton, though invisible to many of the era's larger creatures, was crucial. It fueled fish populations, supported ammonites, and ultimately sustained the giants that roamed the seas. Life was a layered, interconnected system, from microscopic plants to massive reptiles, each playing a role in maintaining the balance of the oceans. Ammonites and belemnites were among the most successful invertebrates, their hard shells allowing them to survive in both shallow lagoons and deep basins. They evolved rapidly, creating a rich fossil record that today allows scientists to track shifts in ocean chemistry, temperature, and geography. The patterns of extinction and emergence among these species often mirrored events on land, as volcanic eruptions, sea level changes, and climate shifts reshaped habitats across the globe. During the Cretaceous, new types of fish emerged, including early forms of teleosts, which would later dominate the modern seas. Sharks, long-established predators, diversified into forms ranging from swift hunters to massive filter feeders. Rays and skates began their evolutionary journey, spreading across continental shelves. Even some marine reptiles adapted to more specialized niches. Some plesiosaurs developed elongated heads for catching fast-moving fish, while certain mosasaurs evolved powerful tails and fins suited for deep diving. The ocean became a theater of endless evolutionary experiments. Climate and geography played essential roles in shaping these oceans. Continental drift split and joined land masses, creating shallow epicontinental seas that warmed under the tropical sun. These warm, nutrient-rich waters became hotspots of biodiversity, where reefs, lagoons, and islands teemed with life. Currents carried nutrients across vast distances, linking distant habitats, while global temperatures influenced oxygen levels and the distribution of species. Life in these seas was both abundant and fragile, dependent on conditions that could shift over millions of years. Even the deep ocean, though less understood, hosted its own forms of adaptation. Hydrothermal vents, black smokers, and deep basins provided habitats for early forms of extremophiles, primitive yet resilient. While the largest marine reptiles dominated the surface and mid-depths, smaller invertebrates, primitive fish, and microorganisms thrived in the unseen depths, maintaining ecosystems largely invisible to the giants above. Life at all levels was interconnected, a complex web that sustained the ocean's diversity. The Mesozoic seas also reveal the impact of mass extinction events on marine life. The End-Triassic and End-Cretaceous extinctions reshaped ecosystems, eliminating many groups while allowing others to radiate and diversify. Ammonites, which survived the Triassic extinction, vanished entirely at the end of the Cretaceous, alongside mosasaurs and other dominant reptiles. These losses opened ecological niches for survivors, driving evolutionary innovation and setting the stage for the modern oceans. The fossil record shows a continuous story of adaptation, resilience, and renewal, emphasizing that the oceans are ever-changing laboratories of life. Life in these ancient seas was not static. Migration patterns, driven by reproduction, food availability, and environmental conditions, created dynamic communities. Schools of fish moved across shallow shelves, following seasonal blooms of plankton. Reptiles traveled thousands of kilometers, seeking prey or suitable breeding grounds. Even some invertebrates displayed long-distance dispersal, carried by currents or floating debris. In this way, the Mesozoic oceans were a world in motion, a fluid, interconnected network that shaped the evolution of its inhabitants. Understanding these oceans allows us to appreciate both the scale and complexity of marine life. The giants, from mosasaurs to ichthyosaurs, captivate the imagination, but the foundation of life, microorganisms, plankton, corals, and small fish, was just as vital. Their interactions, their responses to climate, and their adaptations to predators all contributed to the extraordinary diversity of the age. The Mesozoic seas demonstrate that evolution is not a linear process but a web of interactions, experimentation, and survival, spanning millions of years. Today, as we study fossils, analyze ancient sediments, and reconstruct past climates, we glimpse these lost worlds. We can imagine the power of a mosasaur gliding through a Cretaceous lagoon, the delicate balance of a coral reef, or the shimmering schools of ammonites drifting through Jurassic waters. Each detail tells a story of survival, competition, and innovation, reminding us that life in the oceans has always been creative, resilient, and endlessly fascinating. These ancient seas were also the stage for one of Earth's most profound transitions: the eventual dominance of modern fish and marine mammals after the extinction of the great reptiles. By studying the Mesozoic oceans, we understand the processes that allowed whales, dolphins, and the rich diversity of fish to emerge millions of years later. The patterns of adaptation and ecological opportunity set during the age of dinosaurs continue to influence life in the oceans today. The Mesozoic seas remind us that life's history is written in water. They reveal the power of ecosystems to shape evolution, the influence of geography and climate, and the ongoing interplay between species and environment. In them, we see the creativity of life, the persistence of adaptation, and the enduring importance of the oceans in nurturing complexity. From the smallest plankton to the largest predators, the age of dinosaurs under the sea was a chapter of extraordinary innovation and beauty, a testament to the ocean's role as the cradle of life on Earth. Beneath their surface lies a vast, intricate system of moving water, a network of currents and flows that connect every corner of the globe. These currents are the arteries of the planet, carrying heat, nutrients, and life itself across thousands of kilometers. To understand the oceans is to understand this invisible circulation, known as the global conveyor belt, and its profound influence on climate and ecosystems. Surface currents are driven primarily by wind and the rotation of the Earth. The trade winds push warm waters westward along the equator, while westerlies propel currents eastward in mid-latitudes. These flows form circular gyres in each ocean basin, creating patterns that persist for decades. The Gulf Stream, perhaps the most famous current, carries warm water from the tropics toward Europe, softening winters and regulating weather patterns across continents. Its influence extends far beyond the coastlines it touches directly, demonstrating the interconnectedness of the oceanic system. Below the surface, deeper currents operate on different principles. Differences in temperature and salinity create variations in water density, causing cold, salty water to sink and warmer, less salty water to rise. This thermohaline circulation is slow but relentless, forming the backbone of the global conveyor belt. Water that sinks in the North Atlantic or near Antarctica slowly travels along the ocean floor, resurfacing centuries later in distant seas. Along the way, it carries dissolved oxygen, nutrients, and carbon dioxide, linking ecosystems separated by thousands of kilometers. The conveyor belt is essential for regulating Earth's climate. By transporting heat from equatorial regions to the poles, it moderates temperature extremes, influencing the distribution of ecosystems and the habitability of continents. During the Mesozoic, similar patterns of circulation shaped shallow epicontinental seas, influencing where reefs and planktonic blooms could thrive. Even minor disruptions to these flows can have major consequences, as seen in modern climate phenomena such as El Niño and La Niña, where shifts in surface currents lead to global weather anomalies. Nutrients, too, are carried along these currents. Upwelling zones, where deep, cold water rises to the surface, bring essential minerals and nutrients into sunlit waters, fueling plankton blooms. These blooms form the base of the food web, supporting everything from small fish to massive whales. Changes in current strength or direction can dramatically alter the availability of nutrients, affecting fisheries and the productivity of entire regions. The oceans are thus a living, dynamic system where movement drives life. The deep ocean, often overlooked, plays a crucial role in this circulation. Abyssal plains and trenches act as reservoirs of cold, dense water that slowly flows toward equatorial regions. Hydrothermal vents release mineral-rich fluids that contribute to chemical gradients, supporting unique ecosystems even in the absence of sunlight. These processes illustrate that the oceans are not uniform but structured, layered, and full of interactions that sustain life both at the surface and in the depths. The impact of the global conveyor belt extends to atmospheric systems as well. Ocean currents influence wind patterns, precipitation, and even the intensity of storms. Warm currents can increase evaporation, fueling tropical cyclones, while cold currents can stabilize the air above, reducing rainfall. On longer timescales, shifts in circulation have been linked to glacial cycles and periods of warming, showing that the oceans are intimately tied to the rhythms of Earth's climate. During the age of dinosaurs, ocean currents shaped the distribution of marine life in profound ways. Warm currents allowed reefs and shallow seas to flourish in tropical regions, while cooler currents influenced nutrient availability and plankton productivity in higher latitudes. These patterns determined where fish, ammonites, and marine reptiles could thrive, influencing evolutionary pressures and biodiversity. Currents acted as highways for migration and dispersal, linking ecosystems that might otherwise have remained isolated. Human activity today is altering this ancient system. Warming waters, melting ice, and changes in salinity are affecting the strength and direction of currents. Some models suggest that parts of the conveyor belt, particularly in the North Atlantic, may be slowing, with potential consequences for global climate. Altered currents can influence rainfall, storm patterns, and even the distribution of marine species, demonstrating how sensitive the oceans are to change. Yet, the global conveyor belt is also a testament to resilience. It has persisted through ice ages, volcanic eruptions, and shifts in continental positions. Life has adapted to its rhythms, from planktonic organisms rising with nutrient-rich waters to whales following migratory paths dictated by currents. The ocean circulation is both a force of stability and a driver of change, a dynamic system that shapes life on every scale. Studying currents and circulation reveals not only how the oceans function, but also the importance of their preservation. Disruption of these flows can cascade through ecosystems, altering food webs, species distributions, and climate systems. Protecting the oceans means understanding these connections, recognizing that the movements we cannot see are as vital as the waves we observe. The global conveyor belt is a reminder that the planet operates as a whole, and that every action has consequences across the network of life. Even at night, when the surface seems calm, currents continue their work. Warm water moves toward the poles, cold water sinks and flows along the ocean floor, and nutrients rise to feed plankton and small fish. This hidden motion sustains life above and below, maintains climate balance, and shapes the conditions in which humans, animals, and plants all exist. To ignore the ocean's movement is to misunderstand the very pulse of the Earth. The story of ocean currents is thus a story of interconnection. It reminds us that the seas are not static backdrops, but active, dynamic forces, influencing climate, life, and even the evolution of species over millions of years. By studying them, we gain insight into the past, an understanding of the present, and a guide for the future. Currents carry with them not only water but memory, the memory of geological shifts, climatic events, and the long history of life that has thrived in response to their rhythms. As we close this reflection, one truth stands out. The oceans are alive, not just in the creatures they host, but in the flows, eddies, and currents that shape every ecosystem. They breathe with the planet, redistribute energy and nutrients, and maintain the balance upon which life depends. To listen to the oceans is to witness the heartbeat of the Earth itself, a reminder of the complexity, beauty, and fragility of the world beneath the waves. Oceans are more than bodies of water. They are intricate, interconnected ecosystems, each with its own rules, inhabitants, and dynamics. From shallow coral reefs to the dark, mysterious depths of the abyss, life has found ways to flourish under vastly different conditions. Understanding these ecosystems is to witness the interplay of biology, chemistry, and physics, a dance that has been ongoing for hundreds of millions of years. Coral reefs, often called the rainforests of the sea, are among the most vibrant and productive ecosystems on the planet. Found in shallow, sunlit waters, they are built by tiny coral polyps that secrete calcium carbonate to form complex, three-dimensional structures. These reefs provide shelter, food, and breeding grounds for thousands of species, from colorful fish to crustaceans, mollusks, and sponges. Their diversity is astonishing. In a single reef, hundreds of species may coexist, each occupying a unique niche and contributing to the delicate balance of the system. Reefs are not isolated. They rely on ocean currents to deliver nutrients and larvae, connecting distant habitats and allowing species to disperse across vast distances. Symbiotic relationships are common. Corals host algae that photosynthesize, providing energy for the corals, while fish clean parasites and feed on detritus, maintaining the health of the reef. The productivity of reefs has shaped life for millions of years, creating hotspots where evolutionary innovation accelerates and adaptation is relentless. Beyond the reefs, in the open ocean, life is structured differently but equally fascinating. Phytoplankton, drifting near the surface, form the foundation of the food web. These microscopic plants capture sunlight, convert it into energy, and feed a vast array of creatures, from tiny zooplankton to massive filter-feeding whales. Schools of fish move in coordinated patterns, predators hunt with precision, and countless species undertake migrations spanning thousands of kilometers. The open ocean is both a highway and a hunting ground, where energy flows invisibly but powerfully from one level of life to another. The deep sea, shrouded in darkness and high pressure, presents one of the most extreme environments on Earth. Yet life thrives here as well, exhibiting adaptations that seem almost otherworldly. Bioluminescence is widespread. Anglerfish use glowing lures to attract prey, while jellyfish drift with softly illuminated bodies. Creatures have developed elongated limbs, expandable jaws, and slow metabolisms to survive where food is scarce. Hydrothermal vents support entire communities independent of sunlight, relying instead on chemical energy from the Earth's interior. Tube worms, clams, and unique bacteria form symbiotic relationships, illustrating that life can persist even in extreme isolation. Different ecosystems interact. Nutrients from deep waters rise through upwelling, fueling plankton blooms at the surface, which in turn support fish and seabirds. Coastal mangroves act as nurseries, where juvenile fish can grow safely before venturing into reefs or the open ocean. Estuaries, where rivers meet the sea, are rich in productivity, filtering nutrients and providing habitats for both marine and terrestrial species. The oceans, therefore, function as a network, a web of interdependent ecosystems that sustain life at multiple scales. The age of dinosaurs saw these ecosystems take shape in ways that foreshadow modern patterns. Shallow epicontinental seas teemed with fish, ammonites, and marine reptiles, while coral-like structures provided shelter and feeding grounds. Deeper waters hosted ichthyosaurs and plesiosaurs, hunting prey adapted to open waters and deep zones. These ancient patterns reveal the long continuity of marine ecosystems and the evolutionary pressures that shape species over millions of years. Human activity now challenges these systems. Climate change, ocean acidification, overfishing, and pollution threaten the balance of reefs, the productivity of open oceans, and the integrity of deep-sea habitats. Coral bleaching events are becoming more frequent, oxygen-depleted zones expand, and the smallest organisms that sustain food webs are at risk. Yet the resilience of marine ecosystems remains remarkable. Some species adapt, migrate, or evolve in response to new pressures, and the interconnected nature of the oceans means that protecting one part can benefit many others. Studying these ecosystems reveals both the fragility and power of life in the oceans. Each species, no matter how small, plays a role in nutrient cycling, predator-prey dynamics, and the maintenance of biodiversity. Coral reefs, though covering a small fraction of the ocean, support enormous diversity, while deep-sea habitats maintain cycles that influence global chemistry. Open waters link distant ecosystems, transporting energy and life across thousands of kilometers. Together, these systems form a resilient, interwoven fabric that sustains life on Earth. Observing marine ecosystems also highlights the importance of time. Evolution operates over millions of years, shaping adaptations to temperature, pressure, and nutrient availability. Mass extinctions reset systems, opening niches for new species to emerge. Currents, tides, and seasonal changes continuously move energy and organisms, demonstrating that ecosystems are dynamic, not static. Life in the oceans is constantly adapting, responding to environmental change, and evolving in complexity. Even in the quiet of the night, the oceans remain active. Beneath the waves, plankton drift, predators hunt, and nutrients circulate. Coral polyps feed, deep-sea creatures migrate vertically, and currents carry oxygen and energy across vast distances. The oceans are alive, not only with visible motion, but with countless invisible processes that sustain the planet's climate, chemistry, and biodiversity. Understanding these processes is crucial, as they form the foundation upon which life on Earth depends. The ecosystems of the oceans, from the shallowest reefs to the deepest trenches, teach us about balance, adaptation, and resilience. They remind us that every species matters, every interaction is significant, and that the health of one part affects the whole. They are both ancient and ever-changing, shaped by forces of geology, climate, and evolution, and yet constantly revealing new mysteries. To study them is to witness the enduring creativity of life, the adaptability of organisms, and the profound interdependence of the Earth's living systems. In conclusion, the oceans are a collection of diverse, interlinked ecosystems, each remarkable in its own right but inseparable from the whole. Coral reefs, open waters, and the deep sea each tell a part of the story, illustrating the interplay of biology, chemistry, and physics that has shaped life for millions of years. They are the stage for evolution, the regulator of climate, and the reservoir of Earth's biodiversity. To appreciate the oceans is to recognize their role in sustaining life, shaping climates, and inspiring wonder, a reminder that the world beneath the waves is as vital and fascinating as the lands above. The oceans, in their vastness and complexity, are the lifeblood of our planet. They cradle the history of Earth, holding within their depths the stories of evolution, adaptation, and survival. From the first microscopic organisms that stirred in ancient waters to the sprawling ecosystems of the Mesozoic seas, from the intricate networks of coral reefs to the hidden depths of abyssal plains, the oceans are a testament to life's ingenuity and resilience. To reflect on the oceans is to consider their enormity, not just in physical scale, but in influence. They cover more than 70% of Earth's surface, shaping climate, redistributing heat, and linking continents through invisible currents. Every wave, every tide, every current is a part of a larger system, a network that sustains life, distributes nutrients, and balances the chemistry of the planet. Without them, Earth would be unrecognizable, barren, and inhospitable. Throughout geological history, oceans have been both a cradle and a crucible. In the earliest eons, they nurtured the first forms of life, protecting fragile organisms while providing the chemical ingredients necessary for complex evolution. Cyanobacteria transformed the atmosphere with oxygen, allowing multicellular life to emerge. The Cambrian seas became arenas of experimentation, where trilobites, mollusks, and arthropods diversified into forms that would echo through the ages. Life learned to swim, to hunt, to hide, and to flourish, setting patterns that would repeat and evolve across millions of years. The Mesozoic seas, during the age of dinosaurs, revealed the ocean's boundless creativity. Ichthyosaurs and plesiosaurs hunted alongside schools of fish, ammonites drifted in rhythmic motion, and coral-like structures flourished in tropical lagoons. Each species adapted to its environment, sculpted by currents, temperature, and predation. The oceans were alive with motion, both above and below, forming intricate ecosystems where energy flowed from the smallest plankton to the largest predators. These ancient waters remind us that evolution is a continuous process, shaped by challenges, opportunities, and the invisible hand of natural selection. Modern oceans carry echoes of these ancient systems. Coral reefs remain centers of biodiversity, open waters host complex migratory patterns, and deep seas preserve life adapted to extreme pressure and darkness. The global conveyor belt circulates heat and nutrients, connecting ecosystems across thousands of kilometers, while upwelling zones fuel plankton blooms that support life from microscopic zooplankton to the largest whales. Oceans are living, breathing systems in constant motion, sustaining life and regulating the climate in ways that are both visible and hidden. Yet the oceans are not invulnerable. Human activity has introduced unprecedented pressures. Overfishing depletes species that have survived for millions of years. Pollution, from plastics to chemicals, infiltrates even the most remote regions. Climate change warms surface waters, melts polar ice, alters currents, and acidifies seawater. Coral bleaching events are now frequent, oxygen minimum zones expand, and ecosystems are forced to adapt at speeds far beyond the pace of natural evolution. The oceans remind us that life is resilient, but that resilience has limits in response to these challenges. Humanity is beginning to recognize the ocean's importance. Conservation efforts, marine protected areas, sustainable fishing, and pollution reduction are attempts to restore balance and preserve ecosystems. Scientific research continues to uncover new species, new behaviors, and new interactions, revealing that much of the ocean remains unexplored. Even as pressures mount, the ocean's capacity for renewal and adaptation inspires hope, reminding us that understanding and respect are as crucial as action. Reflecting on the oceans also reveals lessons about interconnectedness. The seas connect continents, regulate climate, and provide food, oxygen, and cultural value to billions of people. Every change in one part, whether overfishing, warming, or pollution, ripples outward, affecting distant habitats, species, and even human communities. The oceans teach us that the Earth is a network of systems, each influencing the other, and that sustainability requires a holistic view that honors these connections. Even in their quiet moments, the oceans speak. The gentle lapping of waves against a shoreline, the deep currents moving unseen, the migration of fish and mammals, the dance of plankton illuminated by sunlight. These are all manifestations of the ocean's pulse. They are a record of history, a mirror of the present, and a blueprint for the future. To listen is to understand that life thrives not in isolation but through connection, adaptation, and resilience as we conclude this exploration. We are reminded that the oceans are ancient and enduring, yet constantly changing. They have survived mass extinctions, climatic shifts, and tectonic upheavals, shaping life on Earth in ways both subtle and profound. They are home to creatures both familiar and strange, ecosystems both delicate and robust, and processes both visible and hidden. The oceans are the cradle of life, the regulator of climate, and a reservoir of mysteries that continue to challenge and inspire you. As to imagine the oceans in their entirety is to appreciate their complexity. The shallow reefs teeming with color and motion, the open waters bustling with migratory life, the deep seas cloaked in darkness but filled with unique adaptations, and the currents that circulate energy and nutrients across the planet. Together, these elements form a coherent system, a living, breathing network that sustains life on Earth. They remind us that our planet is a single, interconnected organism, and that the health of the oceans is inseparable from the health of the Earth itself. The story of the oceans is ultimately a story of persistence and adaptation. From the earliest microorganisms to the giants of the Mesozoic seas, from the productivity of coral reefs to the mystery of abyssal depths, the oceans have continually supported life, shaped evolution, and regulated climate. They carry the memory of Earth's history and the promise of its future. They remind us that life is not static, that ecosystems are dynamic, and that survival depends on balance, resilience, and adaptation, in the quiet moments. As waves ripple across the surface or currents move unseen in the depths, the oceans continue their work. They circulate heat, nutrients, and life, maintaining the systems upon which all terrestrial and marine life depends. To study them is to witness the ongoing story of Earth, to see the interplay of forces that shape climate, ecosystems, and the diversity of life. The oceans are alive, ancient yet dynamic, a constant reminder of the beauty, complexity, and fragility of the planet we call home. As we finish this reflection, one truth becomes clear: the oceans are more than water. They are the pulse of life on Earth. They remind us of the past, sustain the present, and influence the future. They are a source of wonder, a challenge to understanding, and a call to stewardship. In their depths, we find history, innovation, resilience, and mystery. In their currents, we find connection, life, and continuity. And in observing and protecting them, we honor the extraordinary story of Earth itself, a story that began in the seas and continues today, vast, alive, and endlessly captivating.